Good morning all of you. In the previous talk, we had discussed about transistor amplifiers, and then I also said that how the operation amplifier came from the transistor amplifier, and I said that I will disclose the name of the person who is responsible for the development of operation amplifier. So, now I will just spend 5 minutes to recollect what we had done in the previous class. So, in the previous class that we have talked about this transistor amplifier, that is if I have a transistor, then if I want to amplify AC signal, then we had this kind of circuit. So, you had these resistors, here it is grounded, and then we connect the base to this, then we are given a supply voltage here. Now, this is the load resistance, and this is the resistance which is connected in the emitter. The ratio between this and this, for example, if I call this is RL, if I call this is RL and if this is RE. So, the gain of the circuit actually is given by RL by RE. So, for example, I can have here 10K and then I can have 1K, that will give me gain of 10. Now, these two resistors, for example, R1 and R2 are biasing resistors. We said we will select these two resistors to get correct amplification. Normally, this is done by fixing this point, I take this point, fix this initially, without any AC signal. I fix this at midpoint of 15, that is the midpoint of 15 is 7.5 volt. So, I have to fix this at 7.5. So, if I have 10K, then 7.5 have to come here, means around 0.75 milliampere current have to go through this, then same current almost goes through this. That means, if 0.75 milliampere goes, then this voltage will be 0.75 volt. So, we have to adjust these two resistors such that this is sitting at 0.75, that will automatically call for 0.75 plus 0.6, that is 0.75 plus 0.6, that turns out to be 1.35 volt. So, this has sit at 1.35 volt. So, I have to select this R1 and R2 such that this is sitting at 1.35. Normally, we had find we can get various combinations to get from 15 volt. For example, in this case this is at 15 volt. All that need is at this point I have to get 1.35. That will make this point sit at 0.75. This point will sit at 7.5. That is the required starting point. Now, I can get various combination of R1 and R2. Now, the actual value depends upon what is the base current. If I neglect the base current, I can take any value for R1 R2 to get 1.35. But normally, if I take this is 0.75 volt, this voltage, if I take this is 0.75, then the current through this is 0.75 milliampere. Then if HF is 100, then the base current will be 750 microampere by 100, that will be 7.5 microampere. Then I can select the current of 75 microampere here. With that, I can select 1.35 here. So, the 15 divided by the 15 volt divided by R1 plus R2, R1 plus R2 should give me 75 microampere current. So, then we know that 15 into R2 by R1 plus R2 have to be 1.35. So, from this you can get R1 and R2. Then once this R1 R2 is known, then this transistor amplifier is ready for amplification. Now, I can apply AC voltage here, put a decoupling capacitor, so that the DC voltage will not get short circuited through the AC source. Now, I connect AC source. Now, this voltage will be amplified and amplified voltage will appear here. This is the transistor amplifier which we have discussed in the previous class. Now, this is a very simple amplifier, but nevertheless there are issues in this, because it does a good job for AC to amplify AC voltage, but if I want to amplify DC voltage, then we get into problem. For example, if I want to amplify a DC voltage, then I can do one way of doing this would be I can apply DC voltage here. I can apply a DC voltage here, and then this voltage change will produce a DC voltage change here, that will produce a DC voltage change here. Like this we can use this to amplify the DC voltage, but one problem with this is that if I give this and get amplified voltage at this point, this change in voltage represents the change in voltage here. That is, if this voltage changes, I know that this DC voltage also will change. But unfortunately, the change that is taking place at this point is not necessarily due to this alone. This voltage will change even when base emitter voltage of this changes. This base emitter voltage of this will change when temperature of this transistor changes. That means when ambient temperature changes, this point voltage will change. Similarly, if the supply voltage changes, again this voltage will change, because if, for example, if this voltage increases, then this voltage also will increase. If this increases, then this voltage will increase, and that will increase the current through this, and that voltage will decrease. That means the voltage at this point can change due to this change in supply voltage as well as due to change in the temperature of this transistor. This was the biggest problem, and then because of this, to amplify DC, amplifying DC is a difficult job, and then there were various compensation techniques that were used, and even difference amplifier was tried, but then all these things are not very convenient to use. As I said last time, it was the birth of the operation amplifier that actually made the use of the electronic circuits, particularly the analog circuit, very easy, and then electronics started growing only afterwards. So, as I said, this all had started from in 1942 during the Second World War. That is, during the Second World War, they wanted to develop, that is the British Island was attacked by German aircrafts. So, they wanted to develop anti-aircraft system, so that when the aircraft is located in the radar, automatically the gun should be fired and the aircraft should be shot down. That was the thing that they were looking, and the job was actually given to the one Mr. Lobby-Joly, who said that you can develop the so called the present day operation amplifier in 30 days, and then using that MIT with the help of Bell Labs supposed to develop that so called gun director. So, actually what Lobby-Joly done was that he had developed the operation amplifier that can be used to amplify AC as well as DC, and when you amplify DC voltage, the inherent problem that we have discussed so far, that the output voltage can change due to temperature and change due to the supply voltage, that will not be there anymore. And also one need not struggle hard to bias the transistor and then select the resistance and so on. Everything can be inbuilt, and one can use the amplifier as it is. So, that was the job that was given to Joly, and he had done remarkably that work. Now, if you look at that, what is that he had done to solve that two problem? This amplifier was done with 3 vacuum tubes, and now I will not be using the vacuum tube, I will be using the transistor equivalent of that to show the working of that. So, the circuit was quite simple. He had taken 3 transistors and they were connected like that, like this. He had connected this and then this, and this was basically connected to minus 15 volt. This was connected to plus 15 volt. In actual circuit, it was plus 300 and minus 300, this with a vacuum tube, but here we are showing with transistor. Then the third transistor was connected here. And that was the operation amplifier that was used to develop that anti-aircraft. In fact, he had made 300 number of this, and that was hardwired to act as a computer to direct the gun. Now, what you can do is, for example, here this is acting as a this is acting as a non-inverting input of the operational amplifier. This is acting as inverting input of the operational amplifier. Output is taken from here. So, that is this is taken as output V0. Now, for example, if I apply a DC voltage here, I apply for example, I apply with respect to ground here the DC voltage. This is plus 15 minus 15, that means the supply is connected like this, and that is the ground, and that is the input voltage. So, for example, if I apply here say 2 volt, then I connect this to this point. Now, you will be surprised that if I give 2 volt here, if I look at this, I have given now 2 volt with respect to ground. Then if I look at the output here V0, this is also 2 volt with respect to ground, and this 2 volt will not change even if I change this or I change this or at temperature of this or temperature of this or temperature of this, whatever may be the change, this will remain 2 volt as long as this remains at 2 volt. This is what indeed we wanted actually, because this was not achievable in the transistor in a simpler way. Now, let us see how first it is how it is working, and then secondly we see how that even with temperature how this is not changing, and as well even with the varying voltage of this and this, how the output is not changing. These 2 points we have to first understand. Now, for example, if you see the working of this, if I give here 2 volt, I know that this point has to come to 1.4, because base emitter voltage difference is 0.6. So, this is sitting at this is sitting at 2 volt. So, automatically I can say this is sitting at 1.4 volt. If this is sitting at 1.4, then there will be a current through this. Now, this current partly coming from here and then partly coming from here, but however, if I give 2 volt, this has to come to 1.4 and there is some current through this. If there is a current through this, there will be a voltage drop across this. Now, this voltage, the voltage across this resistor is actually nothing but base emitter voltage of this transistor. Now, we know that this is a PNP transistor, base emitter voltage had to be only 0.6 for forward biasing. That means, if there is a current and if that current produces voltage of 0.6 volt across this, then that 0.6 volt will make this transistor forward bias. That means, this will be start conducting. So, then the start conducting means the current will flow through this. Okay. So, that means, if I apply 2 volt, this fellow sits at 1.4, that makes the current flow through this, and that develops a voltage across this, and that voltage applied across this, that across base and emitter of this transistor. That makes this if the voltage is more than 0.6, then this transistor started conducting and the current is flowing through this. Now, as the current flows through this voltage positive voltage will start increasing, and then this gets more and more voltage. Now, assume that this voltage at this point was more than 2 volt, because if I see, suppose if this is more than 2, say assume that I go to 2.1, then what happens? This is already sitting at 1.4, this is this is sitting 1.4, this is 2.1, the difference is 0.7. That is very large, because above 0.6, then enormous current started flowing through the base emitter through the transistor. Now, if I assume this is at 2.1, automatically large current flows through this, and that will make this voltage increase. In fact, what happens if it goes to 2.1, this chap is not going to be 1.4, this chap will go to 0.6 less, that is, this fellow will go to 1.5. If this 1.5, this is 2, this is not going to conduct, because you see this is 1.5, this is 2, only 0.5 volt difference is there. So, this is not going to conduct. If this is not going to conduct, this cannot conduct. If this not conduct, this voltage will decrease. So, automatically what happens, once trying to go more than 2 volt, then this is all the current trying to come through this and very little current trying to come through this. And the other way around, if this voltage trying to go below 2 volt, for example, I take this and put it as 1.9, then if this is 2, automatically this will go to 1.4, this will go to 1.4. Now, if this is 1.4 and this is 1.9, then you have only 0.5 and this cannot conduct. Then heavy current flows through this, then heavy current heavy current flows through this and this voltage increases. So, automatically if this voltage trying to go more than 2 volt, that is if this is 2 volt, if this trying to go more than 2 volt, then that makes automatically this transistor conduct less and then it brings back to 2. In case if this goes below 2, then again below 2, then it makes this transistor to conduct more and this transistor to conduct more and brings back to 2. So, it has no other choice other than sitting at 2. So, automatically that means that if this point is kept 2, then there is no choice other than coming to 2. That is a wonderful thing, because if I fit 2 here, then this also will come to 2. And if we see what happens when temperature changes, even if temperature changes, if this is 2, this also will be 2 only, because if temperature changes, this base emitter voltage also will change, this base emitter voltage also will change. And transistors are very good at tracking, they are almost identical. The difference what it comes in base emitter voltage are second order effect and they are very small. So, with temperature, for example, we know that the base emitter voltage goes by minus 2.2 millivolt per degree C. That means, every 1 degree temperature rise, the base emitter voltage will decrease by 2.2 millivolt, and same decrease taking place here. This also will decrease by 2.2. For example, at 100 degree C or at some other high temperature, instead of at room temperature I need 0.6 volt here difference. At high temperature, assume I need only 0.5 volt. At some other temperature, that means if I raise the temperature by 40 degree, then I will lose 0.1 volt. That means at 25 degree if I need 0.6, then at 65 degree I need only 0.5 volt, and this also needs only 0.5. So, if it needs 0.5, if I give 2 volt here, this fellow instead of 1.4, all that matters is this will go to 1.5, because this needs only 0.5 now. Now, if and this also needs only 0.5. So, this also will settle only at this also will settle at 2 only, because this difference also now only what is required is 0.5. So, that way the temperature drift, the temperature change of temperature of this or this has no effect on the output. Similarly, this base emitter voltage also will change with temperature. It also can require only 0.5 at 65 degree. But then this is not a serious problem, because even if it needs only 0.5 and if this voltage is 0.6, then it will automatically conduct heavily and this voltage will go high. If this goes high, then this will go high and that will make this difference small and this will conduct less. So, automatically the voltage will come down. So, this base emitter voltage has only secondary effect, and that also is not going to affect the output voltage. So, this was a remarkable thing, because the struggle that we had to amplify DC is no more there. We need not worry about the temperature change of this or this. So, if it is 2, automatically it comes to 2. If I keep if I keep this is at some other voltage, for example, I keep this at 4 volt, then this chap also comes to 4 automatically. So, whatever I am giving here, that is followed at this point. Now, we said with temperature has no effect. What about supply change? Suppose supply voltage is plus 15, it goes to 20, no problem. If this goes 20, this trying to also go up. Now, or if the current trying to increase more, then automatically the base emitter voltage will increase, and that will increase the conduction here, and this voltage will go high. If this goes high, then this difference increases, and this, because this will increase, then this will decrease and this current will decrease, and automatically it will pull back. So, either this or this has no effect at the output, and that is good, because whatever I am giving here, that appears here. But what is the use, whatever voltage you are giving here, it comes as it is, which has no effect due to temperature or the supply. But what is the use of getting the same voltage here and here? Because if at all anything to happen, we want to particularly amplify the signal, then how to amplify the thing, that is done very easily. So, what you do is you have the voltage here, instead of directly connecting it here, I will put 2 resistance here, one here and one here to ground. So, if I give here 2 volt, I know this has to come to 2 volt. So, this will be 2 volt for example, I put equal resistance here, this is R and this is R. That means whatever voltage is here is divided by 2, assuming the base current is negligible, that if I had to get 2 volt here, that means I had to get 4 volt here. So, if I give 2 here, this will come to 2 and this will come to 4 volt. And that 4 volt will remain constant, because this 2 volt will remain constant even if the temperature changes or the supply voltage changes, because I had given 2 and this has to come to 2, because if it is not coming to 2 or if it is less than 2, we know that less than 2, then this will conduct heavily and automatically the conduction will increase and it will go up. So, it adjusts to 2 and this automatically goes to 4. So, now we got a gain of 2, I given 2 volt and then I got 4 volt here. If you want different gain, all that I need to do is I have to only change the resistance here or here. If they fix this ratio different, then I will get different gain. For example, if I want gain 10, all that I should do is that I remove this and put 9K and 1K. If I put, for example, I put the resistance here 9K and then 1K. I put here 9K, then here 1K I put. Then if I give for example, here I give 1 volt signal input, then this have to come to 1 volt, and we know that if I have to get 1 volt, this is divided by 10, because 9K and 1K will make a division of 10. So, if I have to get 1K, I have to get here 10 volt. So, this point will go to 10 volt, there is a gain of 10. So, whatever gain you want, you can get it by merely selecting this resistance and this resistance, and you will get output voltage, output voltage which is amplified, this is the input voltage that is amplified with the gain that is determined by this ratio of these two resistance, and the amplified voltage appears here, and this voltage will not change with this or with the temperature, and this can be used both for AC as well as DC, not necessarily that this only for amplifying the DC voltage. For example, if I want to amplify AC voltage, all that I have to do is apply AC directly here. Now, the amplified AC voltage will appear here, and there is no biasing work, no decoupling required, nothing. You give the voltage and take the output here, and this was the first operation amplifier developed by Mr. Joule, and that had solved many problems. It was done during the Second World War, and then this was handed over, as I said, to the MIT, and then they made it as a gun director, and it was a successful project. And using this, they had hit the incoming aircrafts with a 90% success rate, and that was remarkable at that time, and even in today's standard it is very high. But more than that, this was not termed as operation amplifier at the time. It was termed as operation amplifier later, and it was published as termed as operation amplifier and published in a journal almost after the Second World War. Then only people come to know about this, and they were using this. In fact, this is nothing but this is nothing but non-inverting terminal plus input, and this is a minus input of the op amp. If you recall the operation amplifier, the circuit looks like this. We can make it like this, plus minus, and we give the input and then take the output. We are giving the input here. I will show you in the next this thing. So, this same thing we can show. For example, here I show you the equivalent of that and draw bottom for your. So, you have this. And the signal is applied here. And if you see what is the circuit which I discussed so far in terms of this, this plus input is this, and we are given the input here to the ground, and then this the minus input is this. To this we are collected two resistors, this RF and R1. they are nothing but these two resistors. This is RF R1 and this is this output point V0, that is here, and this is plus 15 and that is minus 15 volt. So, we give here this plus 15 and minus 15 volt. Actually, these this is only now simplified and shown like this. So, the gain is now determined 1 plus RF by R1. For example, we have put 9K and 1K, then the gain came 10. So, one can now use this as a building block and then change these resistors to get whatever gain that you want. This was a wonderful thing, and it obviously it is a big hit, and then in fact electronics started growing after this one only. Now, how will we make this one? If it is true, then is it possible to make inverting amplifier in this? Yes, it is possible. For example, we want to make an inverting amplifier. What I do is I will not do this one. I give the ground this below. Then all that I need to do is don't give the input here. The resistance you have. Now what you do? You apply the input signal here. Now at this point you have two contributions, that is one from the signal source, other from the output. Since this is 0, this also have to come to 0. So what happens is that what happens is if if this is 0, this has to come to 0, but at this point you have two contributions, one from the signal, another from the output. So if this has to become 0, for example, I want in this point to be 0, that means this and this has to be out of phase, 180 out of phase, and then the resistance ratio, according to the resistance ratio, the output also have to come in. Now that is what happens in the case of inverting amplifier. So that is birth of operation amplifier. Now okay, then if it is the case, what is that we can do with this? Because we had seen about the use of transistors, we have seen how the operation amplifier had come in and so on. But then what is that we can do with these transistors and operation amplifier? What is that we are studying in this analog circuits? Because if you look at the actual today's use, if you look at the electronic instruments, we see a lot of transistors actually. What happens is that if you will see there are transistors, because then also we see some MOS transistors, then we also see op amps, operation amplifiers, and then we see various resistors, capacitors and so on. Now all these things to be put together, we have to make a circuit, and the circuit supposed to perform given job. Now connecting these transistors, op amps, resistors, capacitors and then sometimes inductors, all these things put together to perform a given job is not a easy job, or not that I can say it is a difficult one. The only thing is we have to understand the rules of the game, because if you have operation amplifier, then we should know what is its limitation. If I use it in a given circuit, how much it is going to be useful, how much error this operation amplifier going to introduce, because we said the operation amplifier is a good thing because it amplifies both AC and DC, and with temperature as well as power supply output is not changing. But then that is a first order effect. But if you go very detailed and see, even op amp output also changes little bit with temperature. So considering all this aspect, we have to design a circuit that will perform the given task effectively. So effectively we should learn what are the rules associated with the transistors, and then MOS switches, and then op amps, resistors, capacitors, inductors and so on, so that we will be able to perform the given job accurately. So that means we have to have various skills associated with various skills to be learned. Now if it is a digital circuit, you have to learn only the logic function, how the logic works, and normally we do not bother much about how the internal circuit is working. and that is not anymore possible with analog circuit. Analog circuit design involves lot of analytical thinking, how to put these components together. We should know the rules of the game, and as well we also should know how much error going to come in the given circuit. For example, if I design a temperature indicator circuit, and if I take the sensor and immerse it, for example, I want measure I want design a temperature indicator circuit. So, if this is my instrument and then I have a thermocouple as a temperature sensor, I connect this thermocouple to the instrument, and this fellow going to display the temperature here, but then it may show as 1000 degree. But then is it really 1000 degree, the temperature here difference between these 2 points, is it really 1000 degree, or is it 980 degree, or is it 1020 degree, or it is 990 degree or 99, what is the error involved. So, one should know the so called error, or the so called what we call as error budgeting, because we have to learn how to do the error budgeting. This is a very important aspect in this. Then second aspect is how to design the circuit here. We had to put various components inside and then make it a working circuit that calls for connecting various components together flawlessly, and then you should not violate any law, and it should work all the time. With all that consideration we have to design this circuit. That needs lot of understanding about the basic circuit. Without that you will never be able to design this thing. So, it needs lot of analytical thinking actually. You need to have a lot of analytical thinking. Without analytical thinking you will not be able to design the analog circuit, because it is not just logic alone. The same one given circuit can be designed in different ways, and each circuit can give different type of error, and then it may cost differently. So, the other aspect is error analytical thinking, that is I should able to synthesize or create a new circuit, and that skill one have to acquire. So, I will say that more than analytical skill, that the circuit design skill is the second aspect you have to learn. Then in fact third is that when you are designing a circuit, we also have to find whether it is optimum or not. So, there are a lot of new techniques involved which will actually simplify our circuit design, in the sense not the question of making it very simple. We can arrive at optimum circuit instead of coming a round off way. So, that actually a lot of new techniques we have to learn. That means, if I have to be a good analog circuit designer, then I should know about error budgeting, I should have the design, I should have the circuit design skill, then I should aware of various techniques involved in understanding in putting the circuit together. So, in this course we will try to learn these three aspects: how to acquire circuit design skill, then how to make error budgeting, and then what are the various techniques involved. These three will put together basis for this course. Okay. Now, let us see what is the circuit design skill. For example, I want to make an LED to go on and off. I want to use a transistor for that. Then I will take an LED, for example, I taken an LED and I want to make this LED to go on off. So, I give it to a power supply. I assume I have only plus 15 volt power supply, and if this LED I want to make this on. Now, for example, if I want to connect, I know that I should not connect immediately to ground. For example, if I put this to ground, then this goes bad, because if you look at the basic concept, if I apply a voltage, LED is like a diode, and then it is forward bias, or during forward bias time it glows. Then depending upon the color of the LED, the current through the LED varies exponentially with the voltage. That means for most of the LED we need to have only 1.8 volt. For example, if 1.8 volt is there, across the LED, you will find about 10 milliampere current is going. If you apply 15 volt, now it is 15 volt applied across the LED, automatically it takes very huge current and then this goes bad. That means I should aware of what is the basic rule involved in connecting the LED. So, what I do is I will not connect this to ground, then I have to somehow make sure that only around 1.8 volt appears across the LED, the rest of the voltage I should make it appear elsewhere. For example, in this case I can put a LED resistance and connect to the ground. If I do this, now the 15 volt is shared between this LED and the resistance that I have it here, effectively seeing that there is a voltage drop here, there is a voltage drop here. This voltage drop plus this voltage drop is actually 15 volt, but nevertheless I want across this 1.8 and the remaining voltage should be across this. That means the remaining voltage in this case is 15 minus 1.8 volt, that comes 13.2 volt, that means 13.2 volt has to be here. But we know that this LED needs about 10 milliampere current for the to glow bright enough, and we should not pass too much current because then the LED also goes bad. So, if I take 10 milliampere is the acceptable current, that I have to get it from the data sheet. In this case I have taken it at 10 milliampere, then since these two are in series, same 10 milliampere current goes through this, and if I have 13.2 volt across this with the 10 milliampere, then I need a resistance value, the R, that actually will be 13.2 divided by 10 milliampere. That 10 milliampere goes minus 3, that is 3. So, that will become 1.32 K resistance. So, if I put 1.32 K resistance here, then I will see that across this 13.2 volt and 1.8 volt and the LED glows and it will not go bad. Maybe the practical value 1.32 K resistance you will not get. So, the acceptable value the nearest one can be 1.5 K or it can be 1.2 K. So, or even it can be say if we want to take it, we will put it 1.5 K, the current will be little less, does not matter because we have no other choice, the nearest resistance that is available is 1.5 K, I can do this. So, we have to, if I want to make the LED to glow, for example, we have to calculate these things, and this type of calculations we will be encountering in analog circuit very often. Now, let us see how to make the LED to go on off using a transistor. For example, what I can do is, now I want to make the this LED go on off using a transistor. So, what I do is I remove this, then I connect this, then I connect the transistor here. For example, I can use transistor in this case to switch on and off, connect this. Now, if I want to make the transistor on, I give a voltage here in the base. If I give a voltage at the base, then there will be a current at the base circuit. For example, there will be a current here, then there will be a current here. So, then LED will glow if sufficient current flows through this. Now, we want a 10 milliampere current through this, and then this is the transistor connected. Another question is how much voltage I have. Assume that I have here another same 15 volt supply is here. Then the question is what resistance I have to use here. Say R1. This is the resistance which we have decided, that is actually 1.5 K. Now, what is the resistance value R1 I have to select, because we have fixed 10 milliampere current through this. If 10 milliampere current I have to go through the collector circuit, we know the base needs some current. The base current that IB is how much, what is the base current we have to find out. Now, to know the base current, I should know the beta of this transistor. Assume the beta of the transistor is 100. So, I see the collector current is 10 milliamps. So, the beta of the beta is ratio between these two. So, automatically IB comes your IC, that is 10 milliampere divided by 100, that is you will have only 0.1 milliampere current flowing here, that is this current is 0.1 milliampere. So, 0.1 milliampere current, it is 100 times amplified, and then 10 milliampere current is flowing through this, and then the LED glows. So, I need 0.1 milliampere. Then the question is, what is the value of R1 I have to select. Now, we know that this is this point is 0, and then we know this point I have to sit at 0.6, because base emitter per forward bias we need 0.6. So, this is 0.6. So, this is 15. So, voltage across this resistance is 15 minus 0.6. So, that is 14.4 volt. So, we have voltage across this resistance turns out to be 14.4 volt, because this has no other goal than sitting at 0.6, because if it is less than 0.6 it will not conduct. If there is no current, then if it is not conductive, there is no base current, then automatically there will not be any voltage drop. So, once you connect like this will automatically come to 0.6. So, that makes this fellow to get 14.4 volt. If it is 14.4 volt, and then we know that what is the required current is 0.1 ampere, then what is the R value I have to put. So, you had this voltage is actually 14.4 volt, and then the current is actually 0.1 amps, then the resistance R that can be calculated, that actually that should give this one 14.4 divided by this 0.1. So, that 0.1 milliamps, sorry, this is 0.1, I is 0.1 milliamps. So, if I take the milliamps here, that actually makes 10 power 3. So, that comes 144 K. So, the if I have this R1, that is this R1, I need 144 K, that will make sure that 0.1 milliampere current is flowing through that. Now, if I see the nearest available value is 120 K resistance available, or I can have 100 K, because if the current goes more than 0.1, no harm. What is required is 0.1 milliampere current minimum, that will make sure your 10 milliampere current is flowing, and we are using the transistor as a switch. We are not operating it in the linear region. So, if we send anything more than 0.1 milliampere, that is no problem. So, if I put 144 K, you will have 0.1 milliampere current. If I put 100 K, a little more than 0.1 milliampere current, that is good, no harm. So, you can select this R1 as a practical value 100 K. So, whenever this 15 volt is applied, LED will glow. If this 15 volt is removed and I connect it to ground, for example, I will put this 100 K here and then connect this to ground, then the LED goes off. Here we are using this transistor as a switch, because in the analog circuit course we will be using transistor or MOSFET as a switch at very many times. So, it is essential that we are aware of these calculations and the importance of this, because many of them have a doubt that if I need 0.1 milliampere, I have to give only 0.1 milliampere. It is not true that you should not give less than 0.1 milliampere. If you give more than 0.1 milliampere, it is no harm, even though it is a waste of current, but it is not a serious problem, nothing happens, the transistor works well, in fact it is better, nothing wrong. So, you give more than 0.1 milliampere. So, instead of saying 0.1 milliampere, we say you need more than 0.1 milliampere. And similarly, if you look at beta, we have taken beta as 100, but then if you look at the data sheet of any transistor, for example, here assume that I had used 3019 transistor, you will say the beta of the transistor is minimum 100. That means I have taken as 100 here, but in actual case the beta of the actual transistor what you had used, even in 3019, 3019 if I take, it may have beta of 100, another 3019 may have beta of 150. When they say beta 100, it is a minimum value 100, no 3019 will have less than beta 100, but anything more than 100 is you have to accept it. You may have a transistor 3019 with beta of 200 also, you may get it when you buy 100 numbers 3019 from one particular company, or 1000 numbers you buy. In fact, most of them will be 150, 200 like that. Only very few will be close to 100, but nevertheless none will be less than 100. So, in this case we always take the worst case parameter that is required, because if I assume beta is the 100 is the here in this case I have taken beta as 100, that is the worst case value. So, if I design with beta 100, then no problem, any transistor I put it will work, because if the beta is more, I need only low current, but anyway I am giving more than required. So, no harm, it works as a switch. So, so this is another important concept we had learn in analog circuit design, that we always going to design a circuit for the worst case, taking the parameters which are worst for that particular case. So, even if I use different transistor, it is not going to affect. That is why it is not necessary, if I arrive at 144K, there is no point in looking for 144K resistance, because in actual case anyway whatever transistor you use, that beta need not be 100, that going to definitely different, going to be more than 100. So, there is no point in calculating the resistance so accurately and putting it there, that has no real meaning, it is only academic interest. So, this should be kept in mind when using the transistor. Now, let us see what are the other things they had done using the transistor earlier, before the operational amplifier had come in. Now, for example, see other application that using transistor they had done was voltage regulators. For example, we might have seen transistor as a voltage regulator. In fact, voltage regulator was designed much before transistor came in, using vacuum tubes only. The first voltage regulator had come in. In fact, it was published in Journal of Physics E in 1930, the voltage regulator using vacuum tubes. But here I will show you how to design how the voltage was designed using transistor, a very primitive regulator. For example, what they had done was they had taken a transistor like this, then they had put the resistance here, then the so called error amplifier was built in here. They put the Zener diode here, and that is the input voltage which is unregulated. This is the unregulated input, and then I have these two resistors connected to this, and that is the regulated output. So, the V0 is the regulated output, and then to bias this, there another resistance is put here. So, this is the, for example, assume that this is 20 volt DC, and this is unregulated in the sense this voltage may be varying, say 20, it may go up to 28, down it may come to 15, assume that this is the case. So, this voltage can be anywhere from 15 to 28, but what I want here is the output to be steady 10 volt, I want steady 10 volt, that this circuit does. Now, if you look at it how it is working, now this is a Zener voltage, Zener diode. Now, if I, for example, I can remove this, that is I put only this. Now, this is nothing but biasing the Zener. So, now there will be a current through this, that will be flowing through this Zener. Assume this is a 5 volt Zener. That means, if sufficient current flows through the Zener, this will set at 5 volt. It will be always 5, it will not change, then it will not change, this will be only 5 volt. Now, how much current I have to pass to keep this one at 5? If current is low, it will go below 5, but it will nevertheless it will not go more than 5. So, I had find out from the data sheet of the Zener what is the neat current of the Zener to get 5 volt. For example, assume that it needs 10 milliampere current to give 5 volt. So, as long as 10 milliampere current goes through that, it will be 5 volt. More than 10 goes, then also it is going to be 5 volt. So, I know that this voltage is going to be minimum 15, it will never go below 15 volt. So, what I do is this is 5. So, I need to have there will be a minimum of 10 volt, that is even in when the voltage is this is 15, there will be 10 volt across this. So, if I take here 1K, for example, here if this I take voltage across, if I take this as 1K, then I know that when this is 15 volt, this is 15, and this will be 5, and then 10 milliampere current will be going, that means 10 milliampere anyway gives 5 volt. So, the voltage across this will be 10, and that will ensure 10 milliampere current even in the worst case. Of course, the voltage goes 28, more current will go, there is no harm, the Zener voltage will slightly increase little more than 5, and at this point of time we take it is only 5. So, this is only biasing the transistor. This these two resistors, this I take R1 and R2, they are only voltage divider, whatever output voltage is there, that is divided, and at this point you get the divided voltage, because if it is, for example, if I put here 10k and here also 10k, then I know that if it is 10 volt I will get 5 volt here. So, whatever voltage there, half of that voltage will come here. Now, I give at this point, now I add the transistor. All that I do is I connect this here, connect this here, and connect this here, that becomes a voltage regulator. Now, I know that this is sitting at 5, even if this current goes also, this always will sit at 5, then I add one more resistance here. So, this is always at 5. Suppose the output voltage goes more than 10, then this will go more than 5. Then we assume that this is gone to 5.6, because if this is at 5, if the transistor have to conduct, this has to come to 5.6, because unless it comes to 5.6, it will not conduct. So, essentially what we are trying is, if this is sitting at 5 and then this cannot go more than 5.6. Suppose if it goes more than 5.6, then the heavy conduction will take place, there will heavy current will flow through this, that current actually comes through this, it goes through this. So, increase in current through Zener not going to increase this voltage, this will sit at 5. So, if it goes more than 5.6, why it goes more than 5.6? Because this goes more than 11.2, because more than twice it goes, then the 11.2 means you will get 5.6. If it goes more than 11.2, this fellow will go more than 5.6. If it goes more than 5.6, then what happens? This will conduct heavily. That current actually comes from here, because this cannot give any current, this can only current can flow here. So, the heavy current will flow through this. If heavy current flows through this, there will be a heavy voltage drop across this, that will make this voltage decrease, because after all voltage at this point is what you have this voltage, say assume this is 20 volt sitting at any given time, 20 volt, and then if I put here for example 4k say 4.7k resistance, then if 5 milliampere goes, you will have 20 volt drop, that will make this fellow 0. If 1 milliampere current goes through this, then you will have 4.7 volt drop. That means, if it is 20 here, 4.7 volt drop will make me to get 15.3 volt here. If 2 milliampere current goes through this, then you will have 9.4 volt drop across this, and then you will have 20 minus 9.4, that will come. So, voltage at this point is nothing but 20, that is supply voltage, minus voltage across this, across 4.7k. Voltage across this depends on how much current it is flowing. So, if more current goes through this, there will be more voltage drop across this, and you will have less voltage here. But whatever voltage is here, that voltage appears here with less by 0.6. So, if this is if this is assume this is coming either come to 10.6, then this will automatically come to 10, because the base emitter voltage has to be only 0.6. So, if it is 10.6, it will come to 10. If it is 20, it will come to 19.4. So, essentially what happens, if more current flows through this, for example, if this voltage is more than 5.6, then more current flows through this, that will make this voltage decrease, that will make this voltage also will decrease, then this also will decrease. In case if this goes less than 5.6, because this is sitting at 5, if it goes less than 5.6, then this will not conduct, or the current flowing through this is very small, then current flowing through this is very small, then less voltage drop occurs across this, you will have very small voltage drop across this, that means more voltage will come here. Other way around, if this goes less than 5.6, less current through this and more voltage at this point, then voltage will go up here also. In case if this goes up and this also will go up. If it goes more than 5.6, then again the conduction will increase and this voltage will decrease and this will decrease. So, eventually if it is set at 5, this have to sit only at 5.6, there is no other go. If you try to go up, immediately this decreases and then this decreases. If it goes below 5.6, immediately this will go up and then this also will go up. So, automatically if I set 5, this will sit at 5.6. If this sit at 5.6, I know that voltage across this 5.6 means the base current is negligible. So, this current and this current are same. So, if across this 5.6 means because across this whatever voltage there only I am here, across this also 5.6. So, you will get voltage of 5.6 plus 5.6, that is 11.2 volt it will come, and 11.2 volt is what it stabilizes here. For example, if I vary this, for example, I can vary this resistance R1, R2, for example, I vary this resistance, then I will find voltage is changing. But nevertheless, this 11.2 will always remain constant, whether I put a load here or I remove the load, whatever it is. If I am not changing this, for example, if I put this and this equal, then I will get 11.2. Suppose if I change this, of course it will change, and it is a good example of showing how the transistor was working. In fact, transistor was used as a voltage regulator, and then this is a simple voltage regulator using transistor, and you can get a regulated output. Of course, it is not a very good regulator. If I change the load, the output will not be strictly 11.2, it will be slightly changing. Similarly, if I change the supply voltage, the output voltage will not be 11 point exact, it will also slightly change. That is because the 0.6 volt what we have taken is not absolutely true, that with the for various reasons this voltage can slightly change. For example, if temperature increases, this 0.6 requirement decreases, at 65 degree it will be only 0.5 degree, 0.5 volt required. So, if this is 5, then this will come to 5.5 and output will go to 11. So, with temperature also output will change a little bit. In fact, if I increase the supply voltage, then this voltage will go high, and then if I have to keep 11.2, then you need more current flow through this, because if it is 28, then you need more voltage drop across. You see, if it is 30, if it is still 11.2, then you need nearly 20 volt across this. If input is 15, then if it has to be 11, then you need only 4 or 5 volt. So, current that I have to go through this, I have to change, then only this point will change. If more current goes through this, then you need more base emitter voltage difference. That means this, if more current I have to go, instead of 5.6 may have to go to 5.61 or 5.62, and that will make this voltage also have to increase. So, that way with supply increase, this also will call for this also will go up little bit. So, like this there are some drawbacks, but nevertheless for as a regulator it is a good one. It was extensively used earlier days, and then in fact even today we use this regulator where regulation requirement is not very tight. Okay. So, we have seen about transistor usage, and then also we have seen how the op amp are born from transistor, and what were the drawbacks of the transistor. The drawbacks of the transistor was the voltage drift and then voltage change due to supply voltage variation. These two are eliminated by using the operational amplifier that was done by Julie. Then also I had shown you this time how to use the transistor as a switch and how to use the transistor as a voltage regulator.